I was told this is an informal talk, so let's get down to it. All right. We'll sleep. No. Okay, so this talk I'm going to give, the first half of it, people will have seen before in Oaxaca way back 2015, 2014. So yeah, haven't really done much since then. But the key word here, right, so the key word is wave packet. So before, when I talked about this stuff, I was looking at plane waves that were incident, and it was all effectively a steady problem. And the new thing here is having a transient wave packet interact with the staircase, which actually introduces some interesting new mathematics, which I'll show you. So the work was done by an internship student from the University of Bremen, who was visiting me for a summer in Edmonton, not the winter, so he was a happy guy. And he did some simulations followed up by some theory. Okay, so the motivation for all this, you're going to see a bit of this next week for sure during their workshop on climate applications of layering. And maybe you've seen some of it in the past. The motivation is in the Arctic Ocean. If you go down roughly 200-300 meters below the surface, and you look at profiles of temperature, this is potential temperature, so it's adjusting for pressure, but it's effectively temperature, and salinity, and you zoom in, you see that you get a staircase pattern. Okay? And so that's the thermohaline staircase, thermo, temperature, haline, salt. So that's the thermohaline staircase. I'm not looking at how it forms or anything else. The question is, it exists. What happens if, say, there's a storm near the surface that launches an internal gravity wave that propagates downward and it encounters this staircase? Okay, and when I go into the details, the whole point is if you have regions of uniform density, then internal waves can't exist. It needs to have background stratification. But if it's a small enough region of uniform density, you can get tunneling. By direct analogy to quantum mechanics, where, you know, it can't exist there, but it can exist above and below, so you might get some transmission through. Okay, so this is just the setup of the problem. This is me, first of all, just going to introduce you to internal waves in case you haven't seen them before. Let's start off with uniform stratification. I'm going to assume throughout that the fluid is incompressible. I'm neglecting viscosity. For this talk, I'm ignoring background rotation, although in the work that we did, we actually did include background rotation. I'm going to do everything in a two-dimensional plane, XZ plane, only with horizontal velocity u in the x direction, w in the vertical direction. And we're going to assume it's a Boussinesq fluid, negligible density change between the bottom and top, but you still must have the density gradient with gravity to create the buoyancy force that drives the waves. So with all those approximations, these are the equations of motion. It's incompressible. We have the x and z momentum equations driven by buoyancy, and we have an internal energy equation. Effectively, it's thinking of temperature and salinity conservation, but mashing it together using the equation of state and casting it in terms of density. So these are our four equations in four unknowns. And then the very first thing I do is I assume the waves are small amplitude so that everything is described by linear equations. Yes, I'm doing linear theory. No comments? Okay, great. Let's move on then. Okay. So if you take those four equations, four linearized equations of four unknowns, combine them, cast it in terms of a stream function psi, then you get this single linear equation that describes the structure as well as the dispersion relation of the waves. Here, crucial quantity is n squared. That's the stratification given in terms of the background density gradient d rho bar dz. Okay, and again, our horizontal vertical velocity are cast in terms of derivatives of the stream function. So if you're dealing with plane waves, you're assuming they're perfectly periodic in x, in z, and in time. You can assume this kind of structure for the stream function with some constant amplitude out front, plug it in, and immediately you get the dispersion relation for internal waves. Is anyone unfamiliar with internal waves? Ish? Probably not. I think everyone is, but I'm still going to go through a pedagogical exercise because I need these concepts for what I'm going to do later. So from the dispersion relation, it always amazes me how much information you get from a dispersion relation. Let's look at waves that are propagating rightward. So k is greater than 0, and the vertical wave number is negative, meaning crests are going downwards. Then in that case, well, in general, you can work out what the phase velocity of the waves is and what the group velocity of the waves are. Okay? And that brings in some bizarre properties of internal waves. First of all, if m is negative and k is positive, then the vertical group velocity has a minus n out front. So this is upwards, but the vertical phase speed is downwards. So the direction of the group and the phase are opposite in the vertical direction. One bizarre property. And the second is if you take the dot product between those two vectors, immediately you see you get 0, which tells you that the group and phase velocities are perpendicular. Hence this plot here that shows a group velocity propagating upward and to the right with the phase velocity going downward and to the right at 90 degrees. And again, in case you haven't seen it, I'm just going to show a couple of movies here, if I can. There we go. So there's a wave packet going up, and you can see the crests going like this, but the group is going up like that. Okay. That's just from a numerical simulation, which is pretty straightforward. But I can also show you this is a lab experiment where I have a set of sinusoidal hills. And I'll say underneath, but the experiment was actually upside down, so they're really at the top, but let's ignore that. We have sinusoidal hills at the bottom of a uniformly stratified fluid, and I tow these hills rightward, and I can tow them at any speed I want. If I tow them slowly enough, then I am forcing the fluid up and down at a frequency set by the tow speed u and the wavelength of the hills. So I force it down, up, down, up. So if I tow it slowly enough, then the frequency at which I'm forcing waves is less than the buoyancy frequency, and I get these propagating waves. This is a visualization method called Schlieren. The background is actually the raw image. This is a processing that lets us see the waves. Let's not get into it, but you can clearly see crests and troughs. And again, if you track that crest moving perpendicular to the line of constant phase, you can see I'm going downwards, but of course the energy is propagating upwards. Okay, so if you're not used to internal waves, that hopefully gets in mind. It's two of those bizarre properties. Okay. One thing we can do with internal waves is write that dispersion relation in terms of the angle theta at which lines of constant phase are oriented to the vertical. So if theta is 0, basically the motion is up, down. In terms of the wave number vector, it's the angle that the wave number vector makes to the horizontal. And so when you write omega as n cos theta, that tells you right away that the frequency of these waves must be less than the buoyancy frequency, or at best equal to it. But I just told you that I can take that hill and pull it as fast as I want. So I can force these waves at a frequency bigger than n, and the question is, what's the consequence of that? And the consequence is you get evanescent waves. So if you tow them very quickly, effectively, you can no longer assume sinusoidal variations in the vertical. It turns out that the vertical wave number is actually a pure imaginary number. And that gamma gives you the e-folding depth of these waves. And hence, if you tow it fast enough, rather than getting sinusoidal variations, you get this exponential decay, which I will also show you from this experiment where we tow these hills rather quickly. And you can see these are basically vertically up and then decaying in amplitude. Lots of turbulence here because they're big hills, and lots of very exciting stuff here of internal waves being generated by Lie wave turbulence, but that's not this talk, so we'll move on. Okay, so those are the main things that I want to get across here. Again, if the frequency is less than n, the waves propagate. If n, especially if n goes to 0, they're evanescent. And that gets us to the tunneling problem. So let's consider, first of all, a simple circumstance where we have a continuous background density, which is linearly changing with height, then it's constant, and then linearly changing with height. So n squared, the background stratification, which is based on the derivative of rho, is basically constant, goes to 0, goes back to a constant. And we will consider an internal wave that is propagating down from above upon this region where it's wave-like above evanescent in the middle, but then wave-like below. This is just like the quantum mechanics problem. I always like to say about quantum mechanics that it's just wave theory. It's absolutely trivial, except the only problem is in quantum mechanics, when you look at it, it suddenly becomes a particle. So my advice to you is just don't look at it, and then it's just wave theory. Okay, so let me show you a lab experiment, which unlike quantum mechanics, lets you see tunneling. You can look at it. So these are two lab experiments. This is an experiment where the background density is a constant gradient with height. Then we mix up the middle part, so it's a constant gradient, close to zero, and then a constant gradient. And I am creating these waves by oscillating a cylinder up there. That's kind of that white region. It's oscillating up and down. That creates a cross pattern of waves, and I'm focusing on the beam that goes downward and to the right. So when this goes downwards, you basically get this beam. There's a transient, of course, but eventually you just get a beam that goes at an angle to the vertical set by the frequency of oscillation relative to the background buoyancy frequency. Here, you see the waves vanish, and then you get a checkerboard pattern there, which is a superposition of the downward and upward propagating waves, and you see this weak transmitted wave. Okay? The reason the waves vanish here is just a technical thing. What we're looking at here is not the amplitude of the waves, but it's actually the derivative of the density, which is just because of the visualization method. And that just means the amplitude, when you look in terms of derivatives, gets really weak compared to what you see with propagating waves. So there you go. You've now seen tunneling perhaps for the first time. Okay, so let's now get into the theory of predicting what is the transmission of these waves across that evanescent layer. And so again, now we're going to specify this n squared background profile constant, the same constant above and below, 0 in the middle. We have this equation, which I showed you before, which just comes from linear theory. But now we're just going to assume that we have periodicity in x and in t, but we don't know what's going on in z. So you plug this into that equation, and that gives you a vertical structure equation. And now, if it wasn't apparent before, you can see exactly why, when the frequency is less than n, this coefficient is positive, and you get wave-like solutions. When the frequency is bigger than n, this coefficient is negative, and you get exponentially decaying solutions. Okay, so that gives you the general vertical structure function. And then the plan is we can solve this piecewise in each of our three layers, top, middle, where it's uniform density, and bottom. And then we need matching conditions to say what's going on at the interfaces between the two. Okay, so again, here are our equations. It's just repeating what I had before. The matching conditions, well, maybe I haven't done that yet. This is just me solving the vertical structure equation. So in the top layer above L over 2, we just had that positive coefficient. I'm going to call that M, and M is that. In fact, that M, if you rearrange it, just gives you the dispersion relation. And then you have these two structures. You have the incident wave coming down and the reflected wave. I'm assuming here that M is positive, which corresponds to negative group velocity, hence the waves are going downwards towards the region. Here, that's a minus M, so these are waves with group velocity going upwards and away from the region. And then, quickly, in the middle region, N is 0, so we just have a minus k squared. That gives us our exponential solutions. And because of causality, we're assuming the wave comes in from the top. We can only have waves go out from the bottom. We can't have waves come in from the bottom. That would be due to some other process. So now we have our vertical structures, but we have all these unknown coefficients. And again, that's where the interface conditions come in to match what's going on between each of these three layers. And the condition in this particular case, because the background density is continuous, is that the stream function and its derivative are continuous. So let's use that information. Here are our conditions at the top interface at plus L over 2 for continuity of the stream function and its derivative. And then at the lower interface at minus L over 2, continuity and its derivative. So what we have now are 4 equations in 5 unknowns. Okay, So our 5 unknowns are the amplitude of the incident, reflected, and transmitted waves, and these 2 constants that say what's going on with the exponential in the middle. So I want to emphasize this is not an eigenvalue problem, because eigenvalue problem, you'd have as many equations unknowns. This is a tunneling problem. And what we are left to do is take these 4 equations and 5 unknowns and eliminate variables so that we can represent, say, how the amplitude of the transmitted wave depends on the amplitude of the incident wave. Okay? So, bit of algebra here. It's maybe not as bad as it looks, because you can say, take that top equation, multiply it through by k, and then add and subtract the equations, and that eliminates the C1, C2. Do the same thing for the second pair, and then you just have equations involving your amplitudes A, which you can eliminate the reflected wave from. So, bit of algebra. After some work, you find out how to relate the transmitted amplitude to the incident wave amplitude. And from that, you can work out the transmission coefficient. Normally, in quantum mechanics, they talk about this is the ratio of the energy of the transmitted wave to the energy of the incident wave. I actually think that's a really wrong way to describe it. It's really the energy flux. It's the wave, the energy, if you want, per time crossing an interface and how much of it gets through. It doesn't actually matter, because the energy flux is just the energy times the group velocity, and the group velocity in the top level is the same as the bottom level, because n squared is the same. But it's a note of caution. If I said the n at the bottom was not the same as the top, if it's slightly different, it would be a different group velocity, and you would not conserve energy unless you're using the energy flux to balance the top and bottom. Anyway, that's all a digression. Here's the expression in terms of the horizontal wave number of the waves relative to the depth of our middle step. And there's that theta, that's the angle at which the waves propagate to the vertical. And this is what it looks like. So that's KL on this axis, and that's the angle of the waves to the vertical on this axis. Okay, so first of all, if L is 0, you don't have a step, then you get perfect transmission. That's the blue colors. Okay. However, and this is a bit surprising, but it comes out of the math, if you have waves that are incident upon this step that are nearly vertical, so the waves are going up and down like this, then if L is tiny, you get virtually no transmission. And consequently, this is maybe less surprising. If the waves are really shallow and they encounter this step, then you get almost no transmission if the step, even if it's very small compared to K. The peak is at 45 degrees. Okay, so that's actually reviewing work that was done almost 20 years ago. So let's advance in time a bit. I want to get to the staircase problem. And in the staircase problem, the density does not vary continuously, but there are steps. In this simple case, to build into it, we're imagining we start off with uniform stratification, and then we mix a middle region of depth L, so it has uniform density. But that, of course, introduces density steps at the top and bottom. The corresponding n squared is exactly the same, except that, in effect, at the interfaces, n squared becomes infinite, because you have an infinitesimal jump in density. But that's all right. We can still do this in a piecewise way, because n squared is exactly the same within each of the layers. I have the exact same functions for the vertical structure. What changes is the matching conditions at the interface. When you have a density jump, it's not that the derivative of the stream function is continuous, but it's this combination that involves the density just above the interface and just below the interface, effectively giving you a reduced gravity, a G prime. That's the combination that must be continuous. And this just pops out of having pressure being continuous across the interface. All right, so let's just go through the procedure again. Here are our equations, now slightly more complicated because we're imposing this condition on the derivative, but involves, again, slightly complicated stuff that introduces G prime, the reduced gravity. Okay, but we have them. We can rewrite it so we can have the transmission in terms of the incident wave, and then find out what the transmission coefficient is, and it's this. Okay, so a little more gross, but that's the answer, and that's what it looks like. And the thing that really stands out, obviously, is this thing. That before, when we said waves were, say, hitting it nearly at a vertical going up and down, that when even if the wave number is really, the depth of the step is really small, we'd have almost no transmission. Well, it does disappear, but then you get perfect transmission if you're bang on that number, which is about 2.4. Okay? And that tongue of perfect transmission actually continues down here, which you can't see. I'm going to come back to that because that's the central point of this talk. But before elaborating on that, let's go up from one step to a staircase. Oh, before I do that, this is the exact same solution, but this is how I'm going to cast my results from now on. Instead of casting it in terms of theta on the bottom axis, I'm actually going to cast it in terms of the frequency relative to the buoyancy frequency. So in terms of cosine theta. This is actually a bit more intuitive. So before, when theta was 0, that corresponds to omega equal to n. The vertically propagated, if they're vertical phase, it means they're going up and down to the buoyancy frequency. That's the transmission spike on the side of the plot when the frequency is the background stratification, and the transmission spike goes down here. The reason it's not just because maybe this is more intuitive, but this is the way we cast it when we put in background rotation in the end, because then we could also have a low frequency cutoff. But again, I'm not going to talk about that. Sorry? So I'm going to get into that. I'll say it briefly right now. It is a resonance between the vertically propagating waves and the interfacial waves you have at these density jumps. So when you have a density jump, if this was continuous, you also have an interfacial wave that has its own dispersion relation, and that peak comes out of this resonance. Okay? Right. Yeah. That's right, and that's because I've designed it. This is the frequency of the incident waves coming in from this stratified fluid from above. So if my frequency was bigger than naught, I couldn't even have these waves come down. Yeah. Yeah, exactly. But that's just because I can't even have an incident wave if omega over n naught is bigger, right? There'd be nothing coming in because it would be evanescent to begin with. Okay. I have not for this, but I have, and I will show you it for the staircase. Okay, so let's do the staircase. And this is just to make the algebra easy. You can do this numerically if the steps are unevenly spaced and they have different density jumps. But to get an analytic solution, I'm going to assume that all my steps are the same depth and all the density jumps in between the steps are all the same. Again, I'm imagining I start off with a uniform background density profile, uniform background density gradient, and I'm mixing regions of the same depth. Okay, so that's my description for the background density over there, and this is the corresponding vertical structure functions. Now I've done something necessary here to come up with an analytic solution. I'm not just writing for the evanescent stuff e to the kz and e to the minus kz. I'm putting in these shifts. And these shifts don't matter. This is just a constant times k. I could roll it into the constant out front, but I'm putting it into those shifts so that when, for example, z is minus jl, it will exactly cancel that plus jl. And when z is minus j minus 1l, that minus jl part still cancels that j. So the point is, when I plug in the interface conditions, I get rid of the j dependence. And so all the structures look the same at the interfaces, as we're going to see in the next slide. Are we happy with that? Okay, great. I pick out the one right at z equals 0. Although again, it doesn't really matter, as it turns out. Okay, so this again had discontinuous jumps, so we have to use continuity of psi and that psi prime minus stuff. At that top interface, it's a half jump in density, as well as at the bottom interface, it's a half jump, so there's a slight factor 2 that comes in there in the G primes, but nonetheless, those are our conditions at z equals 0, analogous conditions at the bottom half step. But in the middle half step, because I've done that little shift with that j minus half stuff, all the j dependence disappears up here. And so for every j, I mean, the j dependence does depend on the coefficients, but nothing in the exponent. So I have this same form for every intermediate step between the top and just above the bottom. And so now I've got a massive number of equations and a whole bunch of unknowns, but we can simplify it. Okay, in fact, I'm just going to go back one. No. In all these cases, say I can divide by k here, and then I get a combination g prime k over omega squared, which is non-dimensional. I have things like e to the kl over 2. I'm going to call that just a non-dimensional quantity. And where I have things like here, where if I divide by k, I'll have an m over k. That's non-dimensional. So I'm going to introduce 3 non-dimensional variables, which will be, where are they? Here, that delta, that m, and that gamma. And that just makes it look nicer. So there's my equations for how the incident wave depends on A1 and B1 are basically the amplitudes of the waves just below the first step. And then I have the AJs, BJs in the middle here that relate one step to the next step. And then I have the AJs, capital Js, relating what's happening right at the interface between the staircase and the stuff underneath. So all that, because I've gotten rid of that J dependence in the middle of things, I can write this whole system as the incident wave amplitude is this mess times our transmitted wave amplitude, where that C is basically a matrix of coefficients from this AJ, is that gamma, gamma over 2, gamma that. It's that matrix right there. And if I have J steps, then this is to the J minus 1. That's because if I have J steps, I have J minus 1 interfaces just below the top and just above the bottom. So that is at least a closed form that relates my incident wave amplitude to my transmitted wave amplitude. And the other nice thing about this is because this is a relatively simple matrix to a J minus 1, I can diagonalize it. No, that's just repeating what I had before. So then, boom, we diagonalize it. We write it as projection vectors and this diagonal matrix capital gamma, which is this, blah, blah. And so now, this is something that AI is just a diagonal matrix to J minus 1, and everything else are just matrices and vectors. Okay. So the algebra is not pretty, but it's tractable. And you can go ahead and work out your transmission coefficient. As it depends on just, again, a ton of variables, all involving these deltas, gammas, and m's. And buried in here are these B naughts, which is actually an important thing, which is a B plus, but the B plus, again, depends on gammas and m's. Okay? So it's a horrible mess, but it is an analytic solution and it's easy to plot. So this is the solution for the transmission coefficient if you have 2 steps and if you have 5 steps. Okay, same as before, I have KL on the vertical axis, omega over N naught on the bottom. Excuse me. You'll notice that when I have 2 steps, I now have 2 spikes hitting the axis, and here I have 5 spikes hitting the axis. Every time I increase the number of steps, I increase the number of resonance peaks that I get. What's really interesting is that boundary doesn't change. Okay? So I'm always modifying what's going on in here, but there's a cutoff between virtually no transmission and high transmission with really strong transmission right on that boundary between the two once you have more and more steps. Okay. So let's just dive a bit deeper into that. Again, this is just showing 1, 2, and 5 steps. If I just take a slice through here and plot as I increase KL, how does my transmission change? This is the plot of transmission versus KL, going from KL being really small, near perfect transmission, and as you approach that critical transition, everything drops down really rapidly the more steps that you have. Okay. What determines that critical transition was that little quantity B0 that appeared in all those equations. And you won't remember what it is, so I'm going to backtrack and show it to you. You got the angles right? Nope. The B0 comes from the eigenvalues of our matrix. We have our B plus, the plus or minus B0, which is importantly square root of B plus squared minus 1. When the discriminant here is positive, then you get decaying stuff. When it's negative, you get oscillatory stuff. And that's why that B0 equals 0 sets the transition between whether you get transmission or everything just decays. Okay.
The solid state physics type question.
Yeah.
In quantum mechanics, if you had a periodic array, completely periodic, then you would get bands and gaps.
Mm-hmm.
Gap.
So not in here because, again, this is a tunneling problem. The eigenvalue problem is what gives you bands and gaps. So if I just looked at natural modes of the system, which I'm going to get to, then you see the idea of having regions of strong transmission or no transmission. Yeah, or if you want to think in terms of light theory, it's like if you have glass with multiple layers on it, which is designed to, say, reflect certain frequencies and transmit other ones. Exactly. Yeah, sure. Another example. Okay, so let's get back to this. So that critical transition is when B0 is 0, and with just a bit of manipulation, if you're assuming the frequency is small, then in fact, this is a simple condition between the frequency and the wave number. It's just a linearly varying, and it holds really well almost up till, in fact, it holds really well up to about 0.9. Omega is 0.9 n. Okay. All right. So now I'm going to have a bit of fun here. See if I can get it right. I want to really focus in on these resonant spikes. These are regions where the transmission is nearly perfect. The other thing I'm going to do, which is slightly different, is I want to look at natural modes of the staircase. Okay? So before, in answer to your earlier question, I was saying the reason you get these resonant spikes is the waves come in and they resonate with the interfacial waves. But I said that qualitatively, and I'm going to try to make this quantitative now, which again comes out with something somewhat non-trivial. So let's start off with the general problem. All of this is the same as before, except one thing. If I'm doing it fully in general, I could also include waves coming in from the bottom. Okay? And so I'm going to consider two special cases of this system. Case I considered before did not have that. That was the tunneling problem. Now let's consider the circumstance where I have perfect transmission to the staircase, which means there's no reflection, B0 is 0, and this thing is still 0. So let's consider that case. I've eliminated one of my variables, so now I actually have two j plus 1 equations in two j plus 1 unknowns. Actually, I think it's two j plus 2 equations and two j plus 2 unknowns, but the point is it's an eigenvalue problem. So I can solve this eigenvalue problem and hence come up with these dispersion relations. Effectively, what is the frequency relative to the wave number such that a plane wave will perfectly transmit to the staircase with no reflection? If you have two steps in your staircase, then you get this black line and you get that blue line. That dotted line is that critical transition I talked about before. You increase the number of steps, solve the problem, and now you get 5 different peaks occurring. And again, you see that one of those peaks is closer and closer and closer to that critical curve. That was that really bright blue band that you see. So that is the case for perfect transmission. For any astrophysicists who think about this problem of wave tunneling through staircases in stars, these are called global modes. And I'm not an expert in this at all, but they're called global modes because these are the modes that from a telescope afar looking at a red sun in the distance, you might actually see these waves because of this perfect transmission characteristic. Okay. Yes. Yes, that was necessary to count the analytic solution, but you can do it numerically with arbitrary thickness. You know, ask that question at the end because I got a bonus slide to actually answer that. Question. Okay, so this is showing perfect transmission, but it's not what I was hypothesizing before. I was saying that the waves are coming in and resonating with interfacial, natural modes of the system. So let's solve this problem differently, not have this coming in and that going out with nothing reflected and nothing coming in from the bottom. The natural mode problem is there's energy in here and it can release energy upwards or release energy downwards. So we're going to solve that problem, just different conditions at the top and bottom. It is still an eigenvalue problem because we've gotten rid of one of our variables and solve that eigenvalue problem. And now you see you get a very similar looking resonant peaks, at least for this highest mode and for j equals 5. But there's something new, and this is the interesting part. The eigenvalues, omega, and consequently also the vertical wave number, is not pure real. It's complex value. And so, to show you the full solution, including the imaginary parts, this, in the dashed lines, is showing you the imaginary part of the frequency. Again, for j equals 2 and j equals 5. There's a lot going on here, and the colors are really crappy. The colors in the dashed lines are meant to correspond to the colors of the solid lines. Solid lines is the real part of the frequency. The dashed lines is the imaginary part of the frequency. Effectively, it is a temporal decay rate. If you put energy into the system and excite a mode, but it's leaking energy above and below, it's losing energy all the time. And that's why it decays in time. But what's really surprising, and I'm not going to go into this, I said the vertical wave number itself is complex. The vertical imaginary part of the vertical wave number corresponds to exponentially increasing amplitude with distance away from the staircase. And that initially is counterintuitive, but when you think of it, it does make sense. These are natural modes of the system. So really, you can go all the way back to infinite time in the past when you had infinite energy in your mode, in your staircase, and then it's decaying in time. And I'm looking at a snapshot now at time t equals 0, but what's happened in all that time is that infinite energy launched enormous waves that have propagated way out to infinity, huge waves, but as it damps down, the amplitude of the waves going away is less. So really you have to think of this exponentially increasing vertical structure as being looking at the time history of well back in time, something really large amplitude was launching enormous waves, and then as time goes by, there's smaller and smaller amplitude. But let's just focus on the growth rate. This is a crucial part for the talk. The growth rate here, you can see here, it's the slowest growth rate, which actually corresponds to the highest vertical structure of the mode. It's somewhat small. As you increase the number of steps, the slowest growth rate, which corresponds again to the mode that's really close to that critical point, is really small. And as you increase the number of steps, the growth rate gets smaller, sorry, the decay rate, I should say, gets smaller and smaller and smaller. And it turns out it goes as the step size to a minus third power. And I hesitated doing this, but I was really happy with this solution, so I'm going to show it to you. You can tune off if you will. That's the equations we're solving to find out what these what the eigenvalue problem is. If you assume k is small and the wave number is really big, so basically you're dealing with low frequency waves that are really shallow, you make those assumptions, then that is your dispersion relation. With tons of gross variables, right? There's all these capital gammas and so on, which are hopefully up there somewhere there, which depends on these j-1 powers of these lambdas, and the lambdas depend on this, which depends on that. Bleh. But the bottom line is, this is a polynomial. And we have to find the roots of this polynomial, which is degree j-1. And you can do it because I just care about this mode that's right close to that critical transition. And at the critical transition, B0 is 0. So I want to look for solutions where this thing is really small. And if it's really small, these capital gammas, once you put in there, you can rewrite the capital gamma as effectively a binomial in B plus and B0 with all these coefficients. But B0 is small, so I don't care about the higher order stuff. I just need to grab the leading order terms here. And so you're basically doing this polynomial expansion to B pluses and B naughts. And again, you're assuming this B naught is small. That's where that occurs. And that's, you can just, again, in this limit where KL is really small, M is really large, your dispersion relation says this goes as 1 over M. So then you can put the M over here, the 2 over there, and say we're not bang on the critical transition, we're close to it by an epsilon. You stick that into those expressions and grab the leading order terms, and you get this expression for how epsilon depends on the step size. And then you take J really large, and that gives you your epsilon with the imaginary part going as J to the minus third power. Okay, lots of algebra to absorb, but that's how you can find a root of this polynomial in your eigenvalue problem because you're close to that critical transition. Anyway, let's move on to simulations. All of that was for plane waves, but what I really wanted to look at was the transient problem of a wave packet incident upon a staircase. So for this problem, because it's a numerical simulation, we cannot have infinitesimal steps. We have to have sharp, but nonetheless resolved steps. And these dots here are showing you the resolution of our simulation, where we, instead of having step jumps, we used a combination of hyperbolic tangent functions to go from one step to the next. Okay, so we'll have a simulation of wave packets incident upon a staircase like this, and we can change number of steps and incident frequency and so on. I'm going to show you two simulations of this. I can find my cursor. Find my cursor. Where are you, little guy? Oh, come on. Let's just try clicking and see what happens. Yay, it works. Okay. So there's our wave packet coming in, interacting with the staircase. This is a zoom in staircase with 2 steps. Also have enhanced the horizontal velocity field, which is what I'm plotting in color. Okay. This diagnostic I want to dive into. What we're doing here in time is we're saying, what's the relative energy above the staircase? That's the reflected part. What's the relative energy below the staircase? That's the transmitted part. And what's the relative energy within the staircase? That's the S part. And so these plots, as it comes in, you start off with everything above the staircase. So it starts off at 1 for reflected and nothing for transmitted or in the staircase. But then you see growth of energy in the staircase, which is the blue line. That goes away, and you see some transmitted, some reflected. Okay. Now let's do the same thing, but have 5 steps. So it goes in, that's the pattern, what's happening in the staircase. And again, you see qualitatively everything's the same, but there's something crucially different here. the energy in the staircase before it just kind of went up and went down symmetrically, but now you see this long decaying tail. That is the resonance of the internal wave packet exciting a natural mode of the system, which holds on to some of that energy. And even after the wave packet's reflected and transmitted, the normal mode is slowly decaying away the rest of the energy. Okay. So that was the new thing that we saw that kind of surprised us. Because of how we've chosen the frequency and the vertical wave number of this, you can also see that the pattern of flow within the staircase is the highest mode. That's basically forward, backwards making within these layers. And that corresponds to the mode that's near the critical transition, which is what we wanted to focus in on. Okay, so results of having measured the transmission coefficient in a number of different simulations where we change, effectively, if you want, changing the step size relative to K, measuring the transmission coefficient. I have a dashed line here is the theory if we have just one step. J equals 2 is if we have 2 steps. And the points correspond to the simulation results. As I go up and add more steps, you see there's a big difference between the theory and simulations. The theory, of course, predicted a transmission spike, but that is the theory for incident plane waves, which neglected this transient excitation of a normal mode that then gives its energy away over a long decay timescale. So what's happening as the wave packet comes in, it excites this natural mode. Some reflects, some transmits, but some still stuck in the staircase, and that equally transmits energy above and below the staircase, which then gives, instead of perfect transmission, it's giving some of that energy into reflection, and hence you don't get that perfect transmission. Okay. And just diagnostics. So if I focus in on this decaying region here, put it up here in a log linear plot, you can see that decay is roughly linear on that scale. And at late times here, it's roughly linear. That means I can measure what is the decay rate. And those pentagons are the measured decay rate. The lines in the circles are theory, that J to the -3 decay rate that was predicted. So definitely it is an excitation of the normal mode that's going on here. One last little word on this, stepping back to the ocean problem. So here's our staircase, and I can come up with a crude estimate for the depth of these steps, roughly 2.5 meters, roughly 20 steps or so in there. If I put in those numbers, then if I have an incident wave coming down with a frequency of 0.1, which is actually kind of fast for a lot of ocean processes, but let's just choose that because I focused in on the talk. That means you would have, if the wave number, and hence the wavelength was 80 meters, you'd be right close to that critical transition, and the decay time would be over a month. So it's some sign that if somehow you have your staircase there and there's some transient process that happens to excite waves with that wave, that frequency, then you would actually see this thing resonating for a long time, which potentially could be something that's observed. Okay. We'll get to your question again later on, Nicole, but typically the largest waves that are created by storms and stuff have much smaller frequencies and much larger horizontal wavelengths. So those would not create this kind of resonance. It really has to be something else. Okay, I'm going to just do 3 more slides, switching gears to a different problem, but it's the same maths. Yeah. So all of this being linear theory, it's not so much disrupt as just perturbs. So we wouldn't have nonlinear effects associated with, say, wave breaking or nonlinear things. Yeah. I should mention, by the way, Nicole's done a lot of this work in analysis of this work from Mary Louise a long time ago, but whatever, I'll move on. Another life. Okay, so I want to talk about tunneling of Rossby waves through a beta plane staircase. Okay? Beta plane staircase, classic examples, think of the alternating winds on Jupiter. And if you really idealize it, you imagine that with these alternating winds, there's associated regions of zero potential vorticity. That's the general definition of potential vorticity in shallow water theory, where you have fluid of mean depth h. Maybe you could have a surface displacement eta. F is the rotation, the Coriolis frequency, and zeta is the relative frequency. You typically ignore the surface deflection, just throw away the eta. The vorticity you can relate to background horizontal density gradients, du, dy, and the Coriolis parameter, you're going to be general, you could say it's a typical value and a linear approximation to it as you go, say, equatorward, or I should say northward, F gets stronger and stronger. And so that's where the word beta comes in, because it's typical to denote this linear approximation to F as F naught plus beta 1. And if you say Q is 0, then you can actually work out what is the U that gives you that, and integrating that gives you stuff that's parabolic in Y. And if you want to make it look a bit more like the theory, you can shift it by some arbitrary amount, setting up so that the mean integrated velocity across the layer is 0, and you get something like that, which looks somewhat like my profiles of density. You have this condition for interfaces between one parabolic profile and another parabolic profile. There's a little cusp where they two meet. And that information is given in terms of how the background velocity gradient changes as you cross that cusp. So this is just an exact copy of my earlier slide onto here. Everything is the same except those red terms. So the mass is all the same. In fact, the delta is exactly the same. I'm stuck with M here, but really L, it should be L, which is the Y component of the, I'll say, meridional wave number. And gamma, of course, doesn't involve G prime anymore. It depends on beta. But the point is, all the maths I did is exactly the same. It's just the symbols have different definitions. So then without having to do any work at all, other than redefine the symbols, you can go on and find the transmission for Rossby waves across a beta plane staircase. This is in the case J equals 5. Exact same formula for the transmission, but just different definitions of gamma M. Okay. So that's what it looks like. And that's actually where I'm going to stop, because this is still something I'm trying to get my head around, if it's even reasonable to look at this and pursue it at all. Yes, thank you very much. Here. There, F. It's virtually the same, just you have a cutoff at F. And if you change the staircases, you still have the spikes. They're just not, they're kind of less even. That's the difference of having uneven steps and including F. Yeah, so basically, you're putting in for the, I'll say, the latitudinal structure equation, there's a U bar in that gives you the various structures. So it does include the effect of the background U chain. Yeah, it's not assuming a stationary fluid at all. Yeah. Of the staircases, they're remarkably robust. Again, Nicole could probably answer this better than I can, but when they were first observed by Mary Louise back in 2004 or whenever it was, she came back later on and the structures were all the same. And what's more, you could go hundreds of kilometers away. I think she might have went 500 kilometers away, and you can map the staircase latitudinally. It's not like there's points where they join and disappear. You can map a stair there to exactly that location, 500 kilometers away. So they're remarkably robust, and again, come back and they're still there, which does get back to a point I keep bringing up with our layering discussions and von Hilliard equations and so on. You don't see mergers with these things. I'm sorry? I'll say greater than 20 years. I mean, that's as long as they've been observed is 20 years. Actually, in the Caribbean, Ray Schmidt had looked at staircases there, same double diffusive phenomena, although it's inverted, it's a fingering layering. So he saw it, but to be honest, I don't think he went back later. He first observed them in the late 1980s, but I don't think he went back, say, 5-10 years ago to see if they changed. So can't comment there, but Mary Louise has gone back repeatedly and has just sees them still sitting there. Yeah, that's a really good point. I think it's a vague memory. Mary Louise is going to be here in a couple of days, so we should all ask her when you see her. I think there were some events where there was like local mixing. Maybe there was a storm that launched a particularly large wave, and it wouldn't be so much tunneling as just there would have been a lot of energy in the system that locally mixed, say over a span of tens of kilometers. But I think she found it just after the mixing event went away, they just re-encroached and rejoined. It's just incredibly robust. Again, I'm going to pause all these questions till Mary Louise comes, because she's not actually giving a talk at our workshop next week, but she's the one who's knowledgeable about this. I can say I think blah, 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 but she can really give you the definitive information.
So with the transient wavepacket, you don't see the resonance.
In terms of the transmission spikes, that's right.
But with the global,
yes, but that's because that's a theory. So in the theory for the global modes, it's a plane internal wave. So in some sense, it's steady in time. It's just constantly coming in, constantly going out. And so what astrophysicists did to model the global modes is they took the same system of steps, except they put on periodic boundary conditions. And then solved the eigenvalue problem for periodic boundary conditions. So effectively, it was just continuous. They didn't have the idea of something coming up here and transiently exciting it. It was just this constant mode.
So now I'm wondering for the ocean, these staircases.
So that's why I put up the numbers there. In theory, with oceanic numbers, you could actually, these things would exist and decay over 40 days. So you could go there and maybe even see the vertical structure and measure it because it's so long-lived, and go back in a week and see that it's still the same structure, but maybe slightly lower amplitude. But the problem is you only get that resonance for these waves that are relatively short horizontal wavelength. And so what's the process that's going to excite the waves with that short wavelength? I mean, I can think of some, but they're really energetic waves in the ocean. Your 100-kilometer horizontal scale, not 80-meter. So I think you might not see it out of the noise. So it remains in theory land. I haven't actually. That's something I want to talk to Laura about. Nope. Wait for it. We'll have it for you by Friday, right, Laura? Thanks, everyone.